Hey, welcome. Today we're diving into something we do, well, every single second of every day, but probably don't think too much about. Reflection. I mean, it's the reason you can see your own face, the reason you can see the moon. It's even how you're seeing this screen right now. So, let's get right into it.
Seriously, have you ever just stopped and wondered what is actually going on there? It feels like some kind of magic, right? A perfect little copy of you trapped behind glass. But here's the thing, it's not magic at all. It's physics. And honestly, by the end of this, you're going to see the world in a completely new light. Literally. And believe it or not, every single reflection you've ever seen, whether it's in a shiny spoon or a calm lake, is all governed by one incredibly simple, really elegant rule. You can almost call it a golden rule for light itself. And there it is, the law of reflection. Now, I know, that sounds super technical, right? Angle of incidence, angle of reflection, but the idea behind it is so simple. It's really just about how things bounce. So let's break down what those terms actually mean.
Okay, so first up, let's imagine a single ray of light, like it's a tiny billiard ball. This ball, our incident ray, is just zooming along in a perfectly straight line until, wham, it hits the side of the pool table. Or, in our case, a surface like a mirror.
So just like that billiard ball, the ray of light doesn't just stop, it bounces right off. And we call this new path the reflected ray. And this is the really cool part. Just like a perfect shot in pool, where that ray goes next is completely 100% predictable.
To really understand that bounce, we need a point of reference. So physicists came up with this idea. Imagine drawing an imaginary line, straight out from the surface at a perfect 90-degree angle, right at the exact spot where the light hits. They call this line the normal. It's basically our ruler for figuring out what happens next.
And here is the absolute heart of it all. The angle between that incoming ray and our imaginary normal line, that's our angle of incidence, or I, is always exactly the same as the angle between the outgoing ray and the normal, the angle of reflection, or R. I equals R. Always, no exceptions. That's the whole law. Pretty simple, right?
Okay, but wait a second. That brings up a pretty obvious question, doesn't it? If that law is always true, why can I see my reflection so clearly in a mirror, but not in, say, this wooden desk? I mean, light is bouncing off the desk too, right? So what's the deal?
And this is where it all clicks into place. On the left, we have regular reflection. Think of a mirror. It's incredibly smooth, so all the light rays hit it and bounce off at the exact same angle, staying perfectly parallel. That's what creates a sharp, clear image. But now look at the right. A surface like paper might look smooth to us, but on a microscopic level, it's full of bumps and ridges. So when light hits it, every single ray still follows the law of reflection, but they all bounce off in a million different directions. They scatter. You get light, but you don't get an image. This is exactly why a perfectly calm lake is a mirror, but the second the wind picks up and makes it choppy, the reflection is...
All right, so we've totally got flat surfaces down. But what happens if we take that flat mirror and we bend it?
Well, bending the mirror completely changes the game. A concave mirror, the kind that caves inward, collects all the light rays and focuses them together onto a single point. That's why your reflection looks so huge in a makeup mirror. It's magnifying you. A convex mirror, which bulges outward, does the exact opposite. It takes the light rays and spreads them out, giving you a much wider field of view. Just think about the side view mirror on your car, the one that says objects in mirror are closer than they appear. That's a convex mirror giving you a wide-angle view of the lane next to you. The law is the same, but the curve is manipulating the light in these really clever ways.
And this simple rule, this idea that I always equals R, isn't just for checking your hair or seeing what's in your blind spot. It's actually a fundamental principle of the universe that we have harnessed to build some of the most important world-changing technologies we have today.
So check this out. There's this super special case of reflection that is just, well, it's mind-blowing. It's called total internal reflection. Here's the deal. If you have light traveling through something dense, like glass or water, and it hits the edge at a really steep angle, the light doesn't escape. It gets trapped, reflecting perfectly back inside. It's like a perfect bounce every single time, with nothing lost.
And where do we use this amazing trick? Well, it's the engine of our entire modern world, fiber optics. The internet, your phone calls, streaming movies, all of it is just data that's been converted into tiny pulses of light. Those pulses get shot into impossibly thin glass fibers, and thanks to total internal reflection, they just bounce perfectly off the inner walls, zigzagging their way across oceans for thousands of miles. So yeah, the next time you're scrolling online, just remember, you're surfing on a wave of perfect reflections.
And it does not stop there.
Giant telescopes use massive curved mirrors to gather faint light from distant stars. Periscopes use a simple set of mirrors so submarines can see above the water. Your car's headlights use carefully shaped reflectors to aim the light onto the road. Projectors, solar furnaces, the list just goes on and on. All of it powered by that one simple law we learned at the beginning.
So to wrap up, we'll leave you with this one last thought. Your eyes, my eyes, they don't actually see objects. They see the light that has bounced off of objects and into our pupils, which means our entire beautiful, colorful perception of reality is built on second-hand reflected information. It really makes you wonder, doesn't it? What does the world truly look like before the light bounces? Something to think about. Thanks so much for tuning in.